In this video, we'll get into just some overall basic review and a few reminders before we get into the actual calculus material. Now, as I said in the introductory video, there'll always be little places, maybe just a little reminder. You may need to go practice solving an equation, a little bit with factoring. And for the most part, just by sticking with the homework, you'll get that practice inside of the actual calculus problems. But some people may decide that they want to go back, flip through the early portions of the book, get a few reminders. And again, I really just have a few things that I want to talk about in this video. The biggest thing is I want to talk about functions and then get a little bit more into the trig functions. So first things first, talking about functions, and again, there are lots of background things to remember. There are aspects about how equations and graphs both connect, but let's get right into the idea of what is a function. Not just looking at an equation or a graph. What is it about that equation or what is it about that graph that makes it a function? And we can go all the way back to first principles and talk about definitions about a function. For every input, there is exactly one output. In math, when we talk about inputs, we're talking about x's. The collection of x's we call the domain. When we talk about outputs, we're talking about the y's. The collection of all y's that get hit, we're talking about the range. So again, a lot of good terms that you'll hear, but focusing on that idea of a function, it's all about the fact that each input goes to one output. For every x, there is only one y to go with it. So before I give you an example of something that is a function, let's start off with something that is not a function. And for that, I'm going to start off with the equation x squared plus y squared equals 9. Now, I don't expect you to remember all the pre-calculus equations to graphs, but as I always say, the more you remember, the better off you are, of course. It's just, always is a little beneficial to remember those things. But if you forget, no big deal. But just thinking about this, how do I know this is not a function? Well, dealing with the equation, that's the hard part. To deal with the equation, I have to think about what happens if I plug in a value for x, how many values do I get for y? So for instance, if I let x equal 0, well, just plugging that in, 0 squared is 0, so I would have y squared equals 9. And now when I solve this, I would take square roots on both sides, and a little reminder, if you take a square root, we get a little penalty in that we have to remember the plus or minus to go with our answer. Now I could come back here, quick reminder about solving equations. If I subtract the 9 from both sides, have this set equal to 0, that would be y squared minus 9 equal to 0. I could factor and solve in that way, but if you solve directly, that's not bad. You just have to remember the plus or minus. And that's evidence that this is not a function. This is not proof, and maybe I got a little lucky with the x value I picked, but that's sufficient evidence. I plugged in one value for x, and I received two values for y. So that tells me that both 0, 3 and 0, negative 3, as xy pairs, both of these xy pairs would be on this graph, and once again, that's the same x going with two different y values. So that's why this is not a function. But now, if we remembered what the graph of this looks like, this would have been a much, much easier exercise. If all I remembered was that this has that very nice basic setup for a circle, specifically this is a circle centered at the origin, and that it represents r squared, so that r would be 3, the radius would be 3. So I would have, as a very rough, quick sketch, that circle would represent this equation. And that's a big deal. That's something I definitely wanted to talk about in this video, because as we move through calculus, we are almost always going to be working with functions, but we're still going to have this back and forth. Are we dealing with the equation or are we dealing with the graph? Typically, the graph is easier. Typically, if we know what we're looking for, we can just look and find it and see it and we're done. But when we're dealing with the equation, we have to be able to apply a certain technique or principle. Because now when I look at the graph, now I can just remember the vertical line test. This graph does not pass the vertical line test. If I draw a vertical line, say over here, or over here, or over here, it doesn't matter where. It doesn't matter that it happened 3 times or 5 times. All it took was that it happened once, but this vertical line is hitting the graph in more than one spot. A vertical line is an x equals line, so that's why we focus on vertical lines. We're focusing on one x value, and if it hits the graph in more than one spot, that is more than one y to go with it. So that's a nice reminder about what is a function. So again, what is a function? We're really getting past some of the mathy terms in terms of more of our general understanding. It's the idea that each x value goes with one y value. And as I do this, everybody, I think you're also starting to see my notes will have a lot more structure. This is just a lot of informal conversation, but you're just seeing what I was talking about in the introduction video. I'm writing things, but I'm saying a lot more. So when you're taking your notes, you may want to be filling some of these extra things in. Over here, I wrote not a function. Why is this not a function? If you are following the argument, there's plenty of good reasons here, but if you are a little behind, or if you go back and forgot that, maybe you want to add a little bit more to your notes. So that's just a quick little suggestion. But now again, back to the idea of, okay, well, what is a function? Well, that's the idea. So our equation would be set up in a way that 1x would only lead to 1y if we had to try and solve. We should be familiar, if we're dealing with a function, we're pretty much always given the y solved by itself, because we're so used to function notation. F of x, g of x, h of x. Once you start seeing that type of notation, you don't have to worry, is it a function? Does it pass the vertical line test? That's already a guarantee. There's no gotcha moments in this class. There's no trickery coming up. You see the notation, you know that you're dealing with a function. So that's just some generic notation. Let me come down to the bottom, and now let's just do a quick exercise that goes with this idea of functions. And that's all I need about functions, and then I want us to talk specifically about the trig functions, and that'll be it for our review. Again, you could always feel free, look back a little more. There's a lot of good information in pre-calculus that's helpful, previous math classes. If you know your factoring is a little rusty or weak, you could go get some practice with that or solving equations. But again, just to hit a few things that we're going to need, and a lot of the other ideas I mentioned, we'll get some of those reminders as we go through the calculus material. So, thinking about a function. And now, again, I had generic notation, but here I'm actually going to do something. So I'm going to first start off with a graph. And even as you see me do this, everyone, I want you to realize I give you the same permission. You don't need graphing paper. I'm just making a sketch. I'm gridding out what I need. I'm doing my little dashes. If these don't represent one unit, you would have to put a scale like this is 2, 4, 6. But with that, it's just one unit. That's all I'm thinking about. And all I want to do is that. By the time we get to calculus, if we don't have a hard point or an open circle, we assume these have arrows and kind of continue in that general trend. But that's not really what I'm going for right here. So here's my generic function f of x. You already see the f of x. Notice if you did try the vertical line test, this function would pass. Every vertical line you draw would only hit the graph in one spot. So this would pass the vertical line test. But I also want to put up an equation. And let's keep that one fairly simple. Let's just do x cubed minus 4x. So if I have these two functions, and this is one of the big reasons why we use function notation. So we can look at multiple functions, whether we're looking at multiple graphs or multiple equations, but that we could use the letter to know which one we're talking about. So this was all given, everybody. I had to give you something to start. So you were given this graph and given this equation, and now here's our first problem and our directions. The directions say evaluate, which in math is often a frustrating term for directions because that typically means do what the notation tells you to do. Well, what is the notation telling us to do? Number one, let's start with evaluate f of 1, and then number 2, we'll evaluate g of 1. So what is this notation actually telling you to do? When you have the generic f of x, that is telling you have a function with an independent variable x. Sometimes it's t, but mostly we'll be using x. And now, this side is all just about notation. The other side, if we have an equation, that's where we would actually do our work. But in problem number 1, that I'm asking you to find f of 1, well, I have to use the graph for that. But what that's really asking me to find is when you look at 1 as an input, 1 is the x value, what is the output, what is the y that goes with it? Well, this is what I was talking about a moment ago. When we've got the graph, we just look. X is 1, so there's the point on the graph that goes with it, and that lines up with a y value of 3. Therefore, f of 1 equals 3. Done. That's it. Nothing more to it. Well, now what about number 2? If I say, what about g of 1? Well, now that tells me to come over here and use the g function. Well, now the g function is an equation, but still what I was saying before, same idea applies. Replacing the x coordinate with 1 is asking you to find what is the y that goes with that x value of 1. Well, when we were looking at the graph, we could just literally look and find it, but with the equation, we have to plug in and do the arithmetic. Do that quickly. 1 cubed is 1, minus 4 times 1 is 4, so 1 minus 4 would give me negative 3. So here's my answer. Both of these technically go with xy pairs. Here's the xy pair we can see, 1, 3 on the graph. Here, if we were going to make a graph for this function, we would have 1, negative 3 would be on that graph. So that would be a point somewhere down here if we were plotting it. But not necessary. That's all we were looking for. But I just make that last point to realize when you give your answer, you don't write it as an xy pair. It's already built into the notation. The x is already right here for you, so that is all we need for the y. Now, I don't want to go too crazy with this. This is just, again, some basic little reminder about how functions work. But let's do that one more time. Let's think about number 3 versus number 4. Let's find the x-intercepts of f of x. And then number 4, we'll find the x-intercepts of g of x. X-intercepts, by definition, where the function touches or crosses the x-axis. Well, one more time, looking at the graph, there's nothing to it. You look at the graph, where does it cross or touch the x-axis? It crosses or touches right here and right here. And those are the only two spots, so this one has 2 x-intercepts, and I'll stick my answer in right here. This one, that is negative 2, 0. Here, just to realize, an x-intercept, a y-intercept, by definition, is an xy pair. So again, bad habit. Some people just write x equals negative 2. You're on the right track. But technically, when you're looking for an intercept that is a point, sort of write it as an xy pair. And similar over here, that one would be 4, 0. So we got negative 2, 0 right here, 4, 0 from right here. Now we could also mention the ideas about interval notation. That's going to come up in this class. And by having parentheses, that's an open interval, the bracket is closed. But context, everybody. This question, it doesn't make any sense to say the x-intercept is this interval. X-intercepts are individual points. If I asked you, where is this graph going down? That would be an interval. It starts going down right after the x value of 1, and it keeps going down forever. So I would say it goes down from 1 to infinity, and that would be an interval. But again, that'll be something else we come back to and we talk about once we get into a lot of the work in calculus. So let's finish this one up and then again get into the trig functions. So x-intercepts of g of x, well, I don't have the graph. So it can't be quite as quick as easy as what I just did right here. That again was just coming directly from looking at the graph, getting the points that I care about. But to realize, well, how am I going to solve for number 4 then when I have the equation? Well, now we need to think about what it really means to be an x-intercept. What's so special about where a point, where the graph touches or crosses the x-axis? And anything that's on the x-axis has a y of 0. So now we're using the idea, and that's all we needed was the actual idea to find it on the graph, but now we're using that and applying it to the equation. So now I would set the y value equal to 0. Either you could make 0 equal x cubed minus 4x. In my experience, more people prefer to put the equal 0 on the right side, but it truly doesn't make a difference here. It's all the same. A equals 0, 0 equals a. It's the same exact thing. Solving this one, well, this one's a little bit complicated. You can't isolate x here. It's already in terms of 0, so I'm going to factor. First, GCF, and x comes out, and then x squared minus 4. That's difference of squares. So now I've fully factored, and now each one of these factors can now be set equal to 0. So now when I solve, I should have given myself a tiny bit more room, but I'll just finish solving in the corner. Well, this one's done. The answer is 0. But putting it back, remember, we started saying y is 0. Now x is 0. So my first answer for this one is 0, comma 0. Here, now I just add the 2, so x equals 2. And 2, comma 0 would be another solution. And last here, I would subtract 2, so x equals negative 2. And negative 2, comma 0 for the final solution. So these 3 are the solutions to this problem. Okay, so again, nice general information about functions. And now let's just get into a few specifics with the trig functions. Again, you're all responsible by having that pre-calculus as a prerequisite, even if you didn't take pre-calculus, maybe by transfer, by placement, plenty of other reasons to be in Calc 1, but you should be familiar with a lot of the basics of trig. So, all I want to do is remind you of several of those basics, and then basically do one big problem that kind of combines several ideas. So, mentioned before, doesn't take a lot. Little bit of trig to do well in the class, and about that much trig to get an A in a Calc 1 class. But for those going into Calc 2, that much trig to pass Calc 2, and it takes a bunch load more. So a lot of people start to get their feet wet here. We'll get to a technique and an idea called the derivative. That'll be a big chunk, but what are some of the other trig facts you should be familiar with? So first thing, trig facts. The first thing I'm going to do is make a reference angle table. I'm going to look at theta as my angle, and I'm going to look at angles 0, 30 degrees, 45, 60, and 90. And I'm going to identify the values for sine and cosine at that angle. One very quick bad habit people have, a lot of people just write sin or cos, and they don't have the sine of theta, the sine of x, the sine of 30 degrees. They just write the letters sin, cos, and without having something after it, technically that's garbage, everybody. So we really want to have that good habit of keep that inner part, that inner argument inside your trig function. So I'm having this set up, and as I fill in, there's a lot of little ways people remember this. I'm just going to fill in the values, everybody. Sine of 0 is 0. Sine of 30 is 1/2. Sine of 45 is the square root of 2 over 2. The square root is just on the numerator, just on the top, not over the whole thing. 60 degrees, sine is radical 3 over 2. Same thing, the square root is just on the top. And then at 90, sine is 1. Cosine, Same values, opposite order. There's a lot of properties and connections between sine and cosine, but I'm going to do same values, just plug them in the opposite order. That is, again, your reference angle table. That only covers angles that takes you through the first quadrant, but going outside the first quadrant, I'll point out ASTC, the different possibilities for where the trig functions are positive, negative. But the truth is, everybody, for Calc 1, we're mostly in the first quadrant. So this chart, I mean, calculators can help with this work as well, but really, especially going into Calc 2, you really should have this chart memorized. Should have enough practice with this that either you could make the chart fairly quickly, just remembering, and a lot of nice little patterns with the values. There's a few other tricks that I show my trig class, but I don't want to get into that. I'd really just rather get to the point of what you need. You, of course, have the advantage in an online format that you could always refer back to this table. But again, going forward, back in an in-person setting, it would be expected that you have this memorized. Now, you don't realize this yet, but as we get going into calculus, you'll start to realize that everything I did here is in degrees, but when we really get into calculus, you cannot use degrees. Everything has to be in radians. So I'm just going to redo this with radians. 0 degrees is 0 radians, but 30 is pi over 6 radians, 45 is pi over 4, 60 is pi over 3, and 90 is pi over 2. That's your first big piece. Second thing. Now, little things, some people use some slightly different, ideas as far as trying to remember all these little pieces. I'm trying to give you one good way, but there's little things some people do that are slightly different. Notice I left a little extra space. I'm going to come back and point out in a moment, some people really like having a tangent line here as well. So I left the room for that to come back in a moment, but I will come back to that in a moment. Next thing, let's talk about the unit circle. A circle, sorry it's a bad circle, but a circle centered at the origin where all angles are in standard form, starting on the positive x-axis, positive angles if we go counterclockwise, negative if we go clockwise. So I'll just do a generic. There would be a theta in the first quadrant, and that any xy pair on this unit circle, x corresponds to the value of cosine at angle theta, y corresponds to the value of sine at angle theta. So right here where we start at 0, that would have an xy pair, 1, 0. Hence, that matches what we saw over here. The x coordinate is 1, the y coordinate is 0 at angle 0. Completely reaffirming what I just said here and how this matches this. But I'm not going to do it everywhere. I mean, that's the little thing. Some people, instead of making this chart, they'd rather make this a little bigger and stick in the 30 degree, 45 degree, 60 degree. Write these as XY pairs, XY, 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 and think of it that way. Again, if that's your preference, that's fine. I'm just giving you a few possibilities, but that's the same information. We come up here. This is the boundary between quadrants 1 and quadrants 2. That's 90 or pi over 2, and that has an XY pair, 0, 1. And again, come over here. Hence, that's why sine is 1 at 90 and cosine is 0 at 90, because again, of this fact with this XY pair. Over here, 180 degrees, or pi radians, that's negative 1, 0. Here at 270, or 3 pi over 2, that's 0, negative 1. And we wrap around our circle, 2 pi is the same as 0. So, why did I do this? A reminder of your xy. And for some people, this is how they figure out the positives and negatives with their trig functions. If you're over here and you're talking about cosine, well, cosine is x. Any x over here in quadrant 2 or quadrant 3 is negative. Therefore, cosine is negative in those quadrants. Or if you're talking about sine and you're up here, Well, any y value up here is positive, therefore sine is positive in quadrants 1 and 2. So that's one way. X connects to cosine, x is positive over here, therefore cosine is positive, x is negative over here, therefore cosine is negative, and similar with sine, but sine would be positive up here in 1 and 2, and would be negative down here in 3 and 4. Other people prefer the ASTC acronym. All students take calculus. There's other clever sayings people have, but it's telling you which trig functions are positive in the quadrant. A stands for all. Everything is positive. All of them are positive in the first quadrant. S stands for sine. Sine is positive in the second. If you're not dealing with sine, then you're not getting a positive in the second quadrant. Tangent is positive in the third. If it's not tangent, it's not positive. Cosine is positive in the fourth. If it's not cosine, it's not positive in the fourth. So again, few little variations there. Some people just use their calculators just to get the plus or minus sign correctly. There's a few places you run into a little trouble with that. So again, that's giving you more of the facts. Just about done with the facts. And like I said, I'm only going to do one problem that uses most of this. So one more quick fact. Well, what about the other trig functions? I only wrote sine and cosine. Over here, I'm only talking about sine and cosine. What about the rest of the trig functions? What we need to know, and truly the only thing we need to know, is that how those other trig functions connect back to the primary two. So that we've got sine, cosine, and a lot of people also throw tangent into the mix for the regular trig functions. So sine, cosine, tangent. But technically tangent is already a combination of these two. Tangent is sine over cosine. But again, it comes up often enough, and that's why, like I was saying a moment ago, some people, I didn't just randomly pick to put sine on top of cosine. I did it that way because if you want to make a tangent line, just divide. 0 divided by 1 is 0, so tangent of 0 is 0. Tangent of 30, well, 1/2 divided by radical 3 over 2. You'd have to clean that up a little bit. You get 1 over radical 3 if you rationalize radical 3 over 3. But again, those are options for you, just at the end to realize 1 divided by 0 is undefined. But again, it comes from this fact. Next, I'll do cosecant, and that is 1 over sine. Secant is 1 over cosine, and then cotangent is 1 over tangent. But wait a second, if tangent is sine over cosine, 1 over, sorry, let me come up here. So cotangent is 1 over tangent, but if tangent is sine over cosine, 1 over sine over cosine, 1 over a fraction, you're multiplying by the reciprocal, but that just simply flips your fraction. So that's your big key, everybody. Those are the key facts. Inside your book, I forget if it's the front or the back cover, but there's a bunch of trig facts, and it's got this and it's got a whole bunch more. But that's what I mean about just some basic trig facts that we're going to need. The other one that comes up a tiny bit, I should have brought that up here, to realize that there's a right triangle inside of here, so I can do an a squared plus b squared equals c squared Pythagorean theorem. But in this situation, that would translate into this distance would be x, this distance would be y, and this distance is 1. So the a squared plus b squared equals c squared becomes x squared plus y squared equals 1, which becomes cosine squared plus sine squared equals 1. The Pythagorean trig identity. We can manipulate this and use this in a bunch of ways. Again, it pops its head up in Calc 1 a few times, not too often. Calc 2, that gets used a real lot. So let's finish this up with a problem. That's it, just one problem. Given sine of theta equals 12 over 13, and I should note that I'm in the first quadrant, but I really just want to keep this more on just the trig values. Given sine of theta is 12 over 13, let's evaluate all the trig functions at theta. How the heck are we supposed to do that? Well, the last fact I didn't put up here is what a lot of people remember as SOHCAHTOA. That if you have a right triangle, the relationships about opposite hypotenuse, adjacent hypotenuse, and which trig function they connect to, that is by far the most important one that we're going to need for Calc 1. Again, this chart, this is helpful. There's a lot of ways calculator can do this for you. There's even technically a few ways the calculator can help you here, but then you're missing the point of the exercise, and that's to try and get you to use SOHCAHTOA. And again, don't worry if you don't know the acronym SOHCAHTOA. It's about making a right triangle. That when I make a right triangle, and I'm just going to arbitrarily make one, I don't care about the size or scale. I'm just drawing this to have a right angle and to put a theta in one of those corners. So from theta's perspective, this is the opposite side, the side directly across from theta. The side directly across from the right angle is our h, our